Welcome to the Deep Dive. Our mission, as always, is pretty straightforward. We take the information you've shared, sift through it, and really pull out the core insights.
And today we've got something quite specific. It's a connection based on these notes and text excerpts about applied calculus.
Yeah, and it's fascinating because it takes calculus, differentiation, integration, stuff you see in class.
And applies it to a really practical, real-world challenge. It moves right past the theory.
Exactly. So this deep dive, it's all about seeing how those math tools help optimize veterinary drug schedules for livestock.
Right. And there's an important twist in the source material. It specifically mentions livestock near fields treated with pesticides.
Ah, okay. So that adds a whole layer of complexity.
Mm.
Makes the timing and the dosage even more critical, I suppose.
Absolutely. That's what the sources imply. Those external factors matter.
Okay, so let's unpack this a bit. The heart of it seems to be using differentiation for optimization, right? Like finding the maximum or minimum point of something.
Precisely. The notes show how you take the derivative of the function describing the drug's concentration over time in the animal. And finding where that derivative is zero, well, that pinpoints the moment the drug hits its peak concentration, its maximum level in the bloodstream.
So you find that specific critical point, as the math folks call it, and that tells you the best time for the drug to have maximum impact.
Exactly. It's not just a guess based on, averages. It's calculated for that drug's behavior.
Makes sense. No more guesswork.
And it goes further. The sources mention analyzing the derivative again, but this time for the elimination phase. Looking at the rate the drug leaves the system.
Okay, so how fast it's clearing out.
That rate of change, the derivative, helps figure out how long the drug stays effective and, crucially, when you might need another dose. It sets that redosing interval.
Right, right. And I guess this is where the pesticide thing comes back in. The sources suggest these environmental factors, like nearby chemicals, could mess with those rates.
That seems to be the implication, maybe affecting how the animal metabolizes the drug or how quickly it excretes it. The text doesn't go deep into the biology, but it flags it as a variable.
So a standard off-the-shelf drug schedule might not cut it in those situations.
Probably not. Using calculus to model it precisely for that specific environment becomes much more important. You need to ensure the drug works, but also doesn't, build up to dangerous levels because something's interfering with its clearance.
Okay. Now, the sources also mentioned integration, didn't they?
Yeah.
Something about the area under the curve.
Yes, the AUC area under the curve. You find that using integration, it essentially measures the total amount of drug exposure the animal gets over a period of time.
And why is that total exposure number useful?
Well, it helps confirm that the optimized schedule, the one you figured out using differentiation for the peaks and rates, actually delivers the right overall therapeutic effect without overexposing the animal. So differentiation finds the critical moments, integration checks the total dose impact, they work together.
So it really drives home that calculus isn't just, abstract equations, it's a practical toolkit.
Definitely. For solving these really complex, dynamic problems in fields like veterinary science, agriculture.
Understanding these concepts, rates of change, optimal points, total accumulation, it's not just for exams. These are skills with direct applications.
Yeah, applications that affect animal health, welfare, and even, the efficiency of our food production.
Okay, so let's wrap up this deep dive. The main takeaway from these sources seems pretty clear. Calculus, especially using differentiation for optimization and integration for total exposure, is vital.
Vital for getting veterinary drug schedules right for livestock, making them precise, effective, and safe.
And as we saw, it's even more crucial when you've got complicating factors, like those environmental pesticides mentioned in the notes. You really need that mathematical precision then.
It demands that data-driven mathematical approach.
It really highlights the practical value, if you're studying calculus, seeing how it connects to real-world issues like this.
Absolutely. And it leaves us with something for you, the listener, to think about. If we get really good at using math like this to optimize drug schedules and improve livestock health, especially in these complex environments, what are the knock-on effects? How might that ripple through the food chain, potentially impacting food safety or even down the line, human health? It's worth considering the wider impact of applying these tools.